introduction. Yeah, okay. Uh, Hello, everyone. Good evening from China side. Okay, today I would present some our recent work on lithium-ion battery aging, degradation mechanism as a rating test and the lifetime predictions. I think firstly, I would like to introduce Xiamen University to you because I think some of you may not familiar with Chinese University. My university located uh, in the southeast part of China. We are located between Shanghai and Hong Kong, and then just operate to Taiwan. And also we have a convenient 6 flights between Paris, Amsterdam, and Xiamen each week. And also we are proud to have some famous battery company in this province, such as CATL, ATL, Empress, and XTC. Maybe you are familiar with CATL, which is one of the biggest battery company in this world, and also XTC is also the major cathode material production company in China. And also you could see that is the Xiamen city actually is composed of several islands. Even that is we call the Gulangyu, the Piano Island. So the Xiamen University also one of the key universities in China, founded in 1921. We have 3 campuses, more than 40,000 students in this university. And my group actually mainly focus on the electrochemical energy storage, for example, lithium battery. And we are introducing some new electrolyte material, including synthesis and the characterization. But also we introduce into build up some in-situ techniques to understand electron reaction mechanism and the interfacial process. So we have published several papers and get some awards. So I summarize our research focus is material, mechanism, and operational test. Before my talk about the lithium-ion battery degradation, actually, my group also have some big interest on the solid-state battery. For example, solid-state lithium-sulfur battery. I think the solid-state lithium-sulfur battery has a very promising future because they're high capacity and also is cheap and environmentally friendly. But the challenge to this battery, including the positive sulfur electrode with high area capacity, is hard to make this not only at a high rate, but also to keep this has a long-term cycle stabilities. So in the last several years, we also using several such as solid-state MR to follow some the dead lithium in solid-state battery, using some electromechanical techniques to follow the pressure change during the cycling of the solid-state battery. And also we develop some the catalyst for sulfur cathodes. We found some single atom cobalt system could work quite well, and also certainly to prevent the big volume change of the sulfur cathodes is also very important to keep the good performance of the batteries. Then I change to my topic today. I think in China we are very interested, or have made some big progress to do some development of renewable energy, such as wind or solar energy. We actually Uh, Probably there's some Chinese word, but anyway, you could read this one. We have actually up to now, up to 2024, renewable energy cumulative installation is more than 1.45 tegawatts. We have even or 2 million related companies working this renewable energy field. And also interesting things that is the China, sorry, it's some typos. Anyway, Chinese electricity storage scale, we actually up to the June 2025, actually we have totally deployed of the gigawatts gigawatt of electricity storage system the from the I think from the 2015 the year-on-year growth is more than 60% percent for each year. Interesting things that is normally we think the pumped hydro storage system is cheaper than the battery storage system. But up to now, actually in China, we have big shares of the lithium-ion battery in the smart grid systems. They have nearly 60%. Other shares maybe including some molten source energy storage, redox flow battery storage, or even air compressed and the lead acid and or the little bit of the sodium-ion battery. But the sodium-ion battery also increasing very fast in the last 2 years. And also we can see that is the fast growth of electricity storage scale in China. You can see that in the last 5 years, that increasing rate is very fast. So that is, you can see the promising future of smart grids for the renewable energy storage. So I think actually it is very important because if we want to use clean energy even for artificial intelligence, we need a lot of the computing station, data storage, or need the energy. But we should say we need a green energy. So I think the electrochemical energy system will play important roles in these systems. So I just quick show some Chinese electricity storage demonstration, like the photovoltaic station, and also some storage staging using lithium-ion battery, and also even some the sodium-ion battery, and also some carbon dioxide compressed station. So if we think about the batteries for smart grids, we certainly, if you think about we need a large number of the battery, so that is the performance cost ratio is very important. So we need a low cost but a high performance of the batteries. So that is, I think, the first factors we should consider. But we'll also need the storage battery can work for a long time. So if normally we say that is 20 to 30 years, because the photovoltaic cells can work 20 to 30 years. So we keep the same pace of the solar cells. And also certainly the safety and also intrinsic or passive safety, intelligent management, battery repairing is possible or not, and even the recycling and the utilization of the battery for smart grids is very important. But as consider the lifetime of the battery, so if you look at the decay battery capacity decay of the battery, it may follow this kind of different types of the curves. So we say that the lifetime of the battery normally should including two types. One is the data driven, we call it black box model because we don't need the detailed mechanism, but we just do some statistic analysis and to do some molecular simulation and get the decay law of the battery. And another model is we call the mechanism-based, also the white box model. They could can predict the life of the battery using the knowledge of the mechanism. So people have used different measurement or characterization techniques to follow the decay of the batteries. So, but if we how to understand the aging and the lifetime or the value of the battery, though, so if we think about the performance of the battery, they should include in several parameters, energy, density, and so on. But it actually is determined by the intrinsic factors that is dependent on the material components, cell manufacturers, and also we can say that the battery is working in some environments, we call some external factors because working protocols and also working environment. And then since the electrochemical reaction mechanism in the battery is very complex, so that is so we how to understand that and using a simple way we could I think this kind of the electrochemical reaction chemical reaction happen in the battery should actually is also determined by the physics or also including some mechanics also chemistry, but the for the material or components, from the view of the material components, actually also determined by the thermodynamic and the kinetic analysis. So we say that is in the thermodynamic way is also the laws of the Lithium inventory, the laws of active material, and also some polarization conditions. That is the polarization shift from the thermodynamic conditions. Okay, that is so the battery agent degradation. So we actually we could for understand or investigate this kind of complex phenomena, we should do a lot of the measurements. We could should do some the cycling testing, calendaring engine, and so on. But from this all of its measurements, actually we should determine the key facts, right? These key facts also we need to do some diagnosis. Actually, that is also this very important to build some model and also to do some prediction or prognosis. That is also the actually for the battery degradation studies. But unfortunately, the universally model for accurate aging prediction under complex conditions remains unachieved. So we need a lot of work to do. So what are the core issues during the battery degradations? You can see this Becker published paper about this 8 years ago. He lists a lot of the side reaction or some unwanted reaction during the cycling of the battery. But so it's complex to understand, but it's also which one is more important. But here, actually, for our studies, we list two key issues we should consider during the battery degradations because if there's no side reaction of the electrolytes, that should be can keep the battery working well because electrolytes that can transport ions from cathode to anode. It just like the blood of the battery, and so that it determines the degradation of the battery, and also that lithium plating that is always happen when you charge at high rate, but it's also not only just delete the active these things also cause some shortage of the battery, also cause some safety issues. So that is very very important factors we should consider during these researches. So for the testing protocol to investigate degradation mechanism, I will show you in the next several slides. We want to evaluate of the battery state of the hills. So we combine electrochemistry and advanced characterizations. We also check the two types of agent modes, a cycling agent or calendar agent that is always met during the agent test. But also we choose three temperatures to check the temperature accelerated procedures. So I show here, actually, you can see that at a different temperature, the decay of the battery, the decay of the capacity decay of the battery exhibit different behavior. If at the room temperature 25 degrees C, that decays quite linearly. But if you increase the temperature to 45 degrees C, that is you can see that is the decrease faster, but also change a little bit at some cycling at some time, especially for the higher temperature such as 65 degree. That is also decay faster, but it's strange even we can jump behavior at the end of the cyclings. So we believe that the temperature increase, battery aging accelerates, but what's the mechanism drive the battery decays? So actually, we divided that stages into three stage. We could see that is we could investigate this degradation stage more clearly. One is the activation stage, because the second one is linear decay stage. Another third one is we call the accelerated decay stage. But all of these all stages actually it is correlated to that loss of active lithium inventory that is linearly with the capacity loss. We believe that is a loss of the lithium inventory in this LFP graphite battery. That is I think that's a major process. That is also interesting. That is where is the loss of the lithium inventory. Actually, if we check SEI using Xion TEM, actually we found that is the loss of the lithium actually go to the SEI on the graphite. The more capacity decay and the more the thicker of the SEI. Certainly, that is, I think, the linear. So we believe that the linear agent is determined mostly by the loss of Li, but for that is nonlinear agent, larger Li or thicker SEI, even some kinetic polarization could result the faster degradation of the battery. That is, the side reaction at the high temperature cause the faster degradation of the batteries. And another issues we must consider that is the calendar agent. Actually, that is hard to investigate because it's not just it's not the only electrochemical reactions. It may including some side reaction that's kind of the chemical reactions, but it still follow that is interesting to see that still follow that linear law of between the LLI and the SOH or the capacity loss. That but at a different temperature that the accelerated rate are different. High temperature, higher accelerating rate. So also see for this one for this kind of calendaring, we also check the thickness, composition, and the mechanical properties of the SAI on the graphite. We found that is at high temperature, larger thickness of the SEI and also more organic and the inorganics. And I think the due to the at the high temperature, faster degradation of the electrolytes, possibly the salts, and then it also cause the stiff behavior of SEI. And also we check that is the time evolution of the evolution of the SEI during the calendaring agent. That is a similar conclusion as before. That is the faster reaction cause the faster rate of the reaction and the faster growth of the fast growth rate of SEI. So that is similar. Consider too that is what kind of the techniques we should some new techniques for this battery degradation. Actually, we explore some okay. You can see we have using Dongguan neutron spallation station. We can even using this experimental setup. We can see that is some movement of the electrolyte between the punch bag and also the gas bag. That is actually, if you can see, that is this kind of the electrolyte movement during charging or discharging process is also very important for the evolution of the battery states, and also it cause actually cause some because it cause some redistribution of the electrolyte in the pore structure, and also even cause some in density change. We believe that it may be due to some SEI changes. We will show some more direct evidence later. And also we also explore the solid operator NMR techniques to follow that is the integration of the lithium ion into the graphite, also even including some you can see that is as increased integration of the lithium ion in the graphite, the different stage of this graphite can see, then also see some lithium plating. That is because the lithium plating, it could cause the faster degradation and even capacity divings. And also, if you check that is time dependent evolution of the different lithiated graphite, also the evolution, the formation of the lithium plating. That is, we can see even use this kind of the differentiate signal, we can even follow the staging process of graphite and also some formation of the lithium dendrite and dissolution of the dendrite. That's so very convenient for combine this time-derived NMR. And then the question is, if we can follow, we can see the formation of this the lithiated graphite and the formation of this lithium dendrite or lithium some others. But could we using some electrochemical methods and to just follow this process? So we also try to use some electrochemical impedance techniques to do some to monitor the dynamic lithium plating evolution, and also we show some kind of the interesting phenomena. So we use this we call the in-situ swelling monitor system combined electrochemical workstation. That's the thermal chamber. That is we try to use that EIS and the thickness pressure measurement construct some multi-dimensional techniques to follow the dynamic evolution of the lithium plating. You can see that is using this we call the dynamic EIS. That is so during this charging process, if we using some equivalent circuit model, we can see that when the potential is below graphite potential below the 0.0 volts. That is lithium, the just the charge transfer of the electrode decrease sharply, but also the double layer of the electrode increase sharply. And also, if we use DRT techniques, we can follow these different reaction times during the charging process. And also, if we can see that is during the charging process, that is the reaction times also change, especially for some charge transfer reactions. That is also the time constant of charge transfer process decrease during the charging process. Okay, so if we using a 2.3 ampere hour punch cell to as a model system to check that is if the charge the cell at the 0.2 C and 0.5 C, you can see that at the higher rate, the lithium plating just can show the earlier lithium plating process. And also interesting thing that is if the lithium plating is less, we can just use the EIS to follow the full process. But if the lithium plating, the amount of lithium plating is large enough, that is actually at the middle or the end of the charging, that is the charge transfer doesn't linearly with with the charge we used. And also, so we use that is we call the thickness measurement. We found that is it could relate it after the EIS could not work. Then you using the pressure techniques can follow this the lithium dendrite, the formation of lithium dendrite. So we could divide it according to these two figures. We can divide it that is lithium plating actually can on graphite could divide it to three stage. One is without any lithium plating and start it at some stage depends on the temperature and also the charging rate. Then the certainly there is at some stage that is correlated quite well with the change of the EIS, also change linearly with charge transfer resistance. But at some stage, that is the pressure measurement can follow further with this of the formation of lead dendrites. That is actually you could understand that because after a large amount of lithium dendrite forms, that is the surface area doesn't change a lot. So that is you cannot see that's linear change of the charge transfer resistance with the amount of the lithium plating. But at this time, the volume change becomes more distinctive. So as we want to, because we want to make sure that our explanation is reasonable, so we're also using the MST techniques to measure that some the dead lithium, we call that is the formed on the graphite electrode, or we're also using some SEM for this stage 1 or stage 2, less the lithium dendrite form that you can not even see from the SEM, but after stage 3, you could see some of these lithium dendrite. So I think the last part of my talk today, I also focus some or some lithium more detail about lithium plating on anodes. So we want to know, firstly, you can see that we certainly know for the lithium plating, we need to know when it will happen, and also then how to monitor it, and also what's the factors drives the lithium plating and anode. And now how can we characterize it? So we think about that. Normally, the lithium plating happens at the fast charging, right? So under fast charging, that is sluggish connects, scrambled the reaction odd at the anode, and then the trigger lithium platings. So that is the for that is the lithium plating apparently is thermodynamic determined reactions, right? But also, but under working conditions, that is also is one kind of the reaction determined kinetically. But even for the kinetically, that is from the bulk diffusion or from the interfacial transfer, and also that is we call that solid phase diffusion or interfacial transfer determine these kinetic factors. So we in this work we try to distinguish that and give some evidence to understand that because lithium for determine the amount of lithium plating actually is has done some have been done in the literature, but the more difficult is which factors determines lithium plating and also lithiation heterogeneity and against lithium plating. But also, I think is quite difficult. So people have used the different techniques, such as spatially resolved X-ray diffraction, to reveal the presence of the lithiation process. And they found that it is the heterogeneity along the thickness directions. And also, even for that is for some optical microscopy, you can see the color change of the graphite is corresponding to the lithiation stage of the graphite, and also that is it is actually there is a strong correlation between the reaction heterogeneity parameters and the onset of the lithium platings. So that is all of the nearly the results present here actually is mostly ex situ techniques. So it's hard to look at the real situation of the graphite cell. So in this work, we using two techniques, two operational techniques to monitor the the lithiation of the graphite and the formation of the lithium metals because for this for operator XRD it's hard to see that is the formation of lithium dendrite, but there is very sensitive it is sensitively probed by the operator MR. So we combine these together, then see what happens at a different charge rate. We found that is from the XRD patterns, we found the higher C rate, the earlier lithium carbon 6 onset happen. That is, if you charge at a high rate, as more lithium carbon 6 will be formed, then you will come to the formation of lithium formation of the lithium dendrite. So that is so we believe that that's the lithium Li LiC6 could be an indicator to the formation of lithium lithium dendrite or lithium plating, because if the lithium the graphite is fully lithiated, they will cause the formation of the lithium plating. That's earlier lithium 6 onset and earlier lithium plating onset, then cause more plated lithium. So that is so consider that is because I think the electrolyte additives are always used in the advanced lithium-ion batteries, but we always think about that is probably the additives can construct the SEI good SEI and make this actually make a good cyclicity of the graphite anode. But actually, it's the not only the to construct additives, not only construct the good SEI, but actually that is could suppress in sometimes could suppress that is the formation of lithium plating or lithium formation of lithium dendrite, because we found that is could cause the lower charge transfer resistance and certainly the lower over potential of lithiation process. So that is so we think that with our results of parental XRD and NMR confirms the additive suppress lithium plating through the optimized interfacial kinetics that it lead to the lithiation more uniformly. If we only think about that is one single particles that cause just improve the interfacial kinetics, but in all of the electrode construct composed of the different single particles, actually the additives could improve the uniformity of the lithiation process. So this one kind of the interfacial that additives could cause the actually affect the lithiation uniformity. But actually, we also think about if the impractical electrode, actually the particles maybe it is that is the one electrode actually are composed of different particle size. So that is so if we consider that not only the interfacial kinetics, we consider different size of the particles. We're using the finite element simulation. That is so that is we could cause that we can found that is when the interfacial kinetics are rate limiting, but also lithiation rates are governed by the particle surface areas. That means the less surface area, and also that is easier to reach the fully lithiated state, and easier to form the lithium plating. That is the kind of the things issues we should consider that. And also for this one, actually, we also that is check our different the SEM to check the formation of lithium plating. You can also see that if we use some FEC additives, that is that's the lithium plating as more uniform, but is for that is high charge transfer resistance charge transfer resistance case. That is for the baseline electrolyte. You can see a larger lithium plating. That is better in facial kinetics, cause more uniform lithium plating. But so that is if we want to suppress this kind of the side effect or the particle size distribution, so we need also may need to construct some the electrodes with optimized the size distribution of this or size distribution of the particles. You can see that is the less size distribution of the particle, they cause easier lithium plating, and also that is also not only for this for this kind of the simulation. We could also to simulate this kind of the situations. Okay, now finally, I don't have time to distract more about lifetime prediction of the battery, but I think the artificial intelligence will play more important roles in the future, including to some if we want to construct the multi-condition battery health management framework, we need to do some agent condition identification first and do some mechanism promote to understand what happened in the battery and do some SOH estimation using the data and the artificial techniques. And then we hope in the future we can construct some generalized model and to fit our just with practical use of these models. I think I come to the end of my talk. I just want to share some message that electrochemical energy storage have gradually become an essential component of the energy internet or supply consumption technology. I think the development of the high safety, long cycling life, and intelligent battery requires interdisciplinary collaborations, because you can see that for electrolyte deletion and lithium plating and even some particle cracking of the battery could cause the faster decay of the battery. But for this kind of the investigation, we need multi-scale and multi-physics models to understand the intrinsic reason of this decay of the batteries. So we believe that, I believe that next generation battery, that should be knowable, measurable, controllable, and predictable. That is very important for our battery with some intelligent scale. Or we may construct some intelligent battery in the future, as I believe. So in this talk, we have shown that the two key degradation factors, lithium plating and electrolyte degradation, is actually very important core issues for the for understanding of the degradation of the lithium battery. It causes a faster or rollover degradation of the batteries. And finally, I would like to thank my groups, my colleagues, my groups, and also my sponsors. Thank you very much.